Welcome everyone. In this video I'm going to show you how to solve exercise number 1.5. Yesterday at the exercises session we didn't have enough time to go through exercise 1.5 and therefore I am going to discuss it in this short video. Let's read it together. In class we worked out the expectation values of the energy, momentum and position for an electron confined to a box of size L in one dimension. Now calculate the same set of expectation values for an electron with periodic boundary conditions in one dimension. So we are considering a particle in a one-dimensional box of size L with periodic boundary conditions, which we discussed yesterday, and basically mean that the wave function must be periodic with period equal to L. So psi computed at x plus L must equal psi computed at x. This implies, after solving the Schrödinger equation, that psi of x takes the following form: a times e to the I kx, with k identified from the periodic boundary conditions, and the allowed values of k are 2 pi over L times an integer n. So n can take the values 0, plus or minus 1, plus or minus 2, and so on and so forth. The exercise asks to compute the energy, momentum, and position expectation values. So let's start from the energy. The expectation value for the energy, as a definition, is the integral of psi of x star, so the complex conjugate, times the Hamiltonian h applied to psi of x. Now h in our case is d minus h bar square divided by 2m, the second order derivative with respect to x. In principle we should have also plus v of x, but v of x is equal to 0 for us inside the box. Therefore our operator, our Hamiltonian, is just the kinetic energy, which is proportional to the second order derivative. Okay, so the integral is performed over the x, and it runs from 0 to L, which are the boundaries of our box. Let's compute the integral. So integral from 0 to L of psi of x star, which means a star, times e to the minus I kx, and then the second order derivative, the minus h bar square divided by 2m, the second order derivative of a e to the I kx over the x. Now, each derivative brings down a factor of ik. Therefore, the second order derivative takes a factor of ik twice. So it brings down a factor of ik to the square, which is equal to minus k square. And therefore we have the integral from 0 to L of this constant goes out of the derivative, and we can bring it together with A star to give square modulus of A, then e to the minus I kx times e to the I kx, which comes from the derivative, gives 1. And we still have a minus k square, so at the end we are left with h bar square k square divided by 2m integrated over dx, which means that our final result is equal to h bar square k square divided by 2m, because this integral here is equal to 1 due to the normalization condition of the wave function. So the expectation value of the energy is h bar square k square divided by 2m, as one should expect, because the wave functions that we are substituting in our integral, so the wave functions over which we are computing the expectation value of the energy, are eigenfunctions of the Hamiltonian. So they are eigenfunctions of the energy operator, let's say. And therefore, the expectation value must coincide with the eigenvalue of that state. Now, the expectation value for the position and the momentum, we can compute them. We start from the expectation value of the position of the momentum operator, so P. I remind you that the operator P is equal to minus I h bar d over dx. So it's proportional to the derivative. And therefore, the expectation value of P is equal to the integral from 0 to L of, again, the wave function complex conjugate, so A star e to the minus I kx times minus I h bar, and then the derivative over x with respect to x of A e to the I kx integrated over dx. Similarly to what we did before, we can bring out the constant A, which we can multiply by A star, giving us A square modulus. The derivative takes a factor of ik down times e to the ikx. So we have ik times minus ih bar, and the e to the ikx that comes from the derivative, if we multiply it by e to the minus ikx, we get 1, and therefore this is the final result. At the end, I times minus I gives 1, and therefore we have h bar k, and the integral over dx from 0 to L of square modulus of A gives 1, for the same reason that I said before, so due to the normalization condition of the wave function. You can see it here. So the expectation value of P, the momentum operator, is h bar k. We will come to this point later on. Finally, the expectation value of the position operator x is given by the integral from 0 to L of psi star of x times psi of x in dx. By substituting psi of x with the correct form of the wave function, we have the following. This operator, the operator x, is quite simple compared with the Hamiltonian and the momentum, because it doesn't take any derivative of the wave function it is acting onto. So we can just bring these factors, this quantity here, the wave function on the left, and compute the multiplication. So a times a star gives a to the square, e to the ikx times e to the minus ikx gives 1, and therefore we end up with the following integral. So we have basically a square modulus times the integral of x, which is x squared divided by 2, computed from 0 to L, and therefore the result is a square modulus times L square divided by 2. Now a square modulus has to be equal to 1 over L for the normalization condition, and therefore the expectation value of x is L divided by 2. So to summarize, the expectation value of the energy is h bar square k squared divided by 2m. The expectation value of the momentum operator is h bar k, and the expectation value of the position operator is L divided by 2. So concerning the position operator, it's quite intuitive that its expectation value is L divided by 2, because since our system is symmetric, meaning that our box is symmetric left compared to the right, the expectation value has to be at the center of our box. So since our box extends from 0 to L, it's intuitive, it's understandable that the expectation value of x stays exactly at the center of the box, so at L divided by 2. Now, in the second part of the exercise, let's read it together. Compare your solutions for the two cases, remembering that both are described by the same Schrödinger equation with v equal to 0, and the only difference is the choice of boundary conditions. In particular, think about and comment on which of the two wave functions are eigenfunctions of the operators for energy, momentum, and position, and why. This should give you some greater insight into why periodic boundary conditions are a better choice for electrons in solids. So, if we compare the results that we get for periodic boundary conditions that we have here on the left, with the results that we have with the standing waves, so the boundary condition such that psi of x equals, psi of 0 equals psi of L equals 0, which comes from the problem without periodic boundary conditions, so with infinite energy, potential energy walls at x equal to 0 and x equal to L. In that case, we have that the expectation value of the energy is still h bar square k square divided by 2m. The expectation value of the momentum operator is 0, and the expectation value of x is equal to L divided by 2. You see that in both cases the expectation value of the energy and the expectation value of the position are the same. The explanation is quite simple. Concerning the energy, in both cases the wave function is a solution of the Schrödinger equation, and therefore the wave function itself is an eigenfunction of the energy operator, of the Hamiltonian. And therefore the expectation value of the energy corresponds to the eigenvalue associated to that wave function. So at the end, since the two eigenvalues take the same form, h bar square k squared divided by 2m, so does the expectation value. The difference coming from the boundary conditions is we find it in the allowed values of k. So if we were to plot the allowed values of the energy, we would find a difference in the two cases because the allowed values for k are different, but the functional form is exactly the same. Concerning the position, so the expectation value of the position, the results have to be the same both in periodic boundary condition and with the standing waves. Because again, in both cases our potential is symmetric, our box is symmetric, the left part is equal to the right part. If we imagine to divide in two parts the box, the left side is the same as the right side, and therefore the mean value of the position has to be at the center of our box. And this is the same, this argument holds for both periodic boundary conditions and for the infinite wall case. And finally, the momentum operator, which is the one where we observe the main difference. So you see that in the two cases we have two different expectation values. The point here is that while in periodic boundary conditions the waves that we have, the wave functions that we have, can be so-called traveling waves, which means that they have a given velocity, so they can have a non-zero momentum. In the standing wave case, the expectation value of the momentum has to be zero. Why? Because standing waves, if you remember from the general physics classes, standing waves are defined as a superposition of a wave that travels forward and a wave that travels backward in such a way that the resulting wave is standing, so it is not traveling. It has some fixed points, which are the ones at x equal to 0 and at x equal to L, and at the end the momentum, so the velocity of this wave, has to be 0. So the main difference between the infinite wall case, where we have standing waves, and the case with periodic boundary conditions is that their solution are two different kind of waves. In one case they are standing waves and therefore have no velocity, and therefore the expectation value of the momentum is 0. In the other case they can be traveling waves, and therefore the expectation value of the momentum operator can be non-zero, and it is indeed equal to h bar k. Now there is more than that actually. Indeed, if you look at the wave function and you try to apply the momentum operator to it, let's see what happens. So in periodic boundary conditions, in periodic boundary conditions, the wave function psi of x is equal to a times e to the I k x. For the standing wave case, instead, the wave function reads psi of x equal to a times sine of kx. So if we apply the momentum operator p equal minus I h bar d over dx to the two wave functions, we see that minus I h bar times a e to the I kx, sorry, d over dx, I forgot the derivative, is equal to minus I h bar a times I k times e to the I kx, right? So it is equal to h bar k times a e to the I kx. But this one is psi of x, and therefore this is equal to h bar k psi of x. So we just proved that p applied to psi of x equals h bar k psi of x. You see that this is an eigenvalue problem. It means that psi of x, the psi of x that we used, is exactly the eigenfunction of the momentum operator with eigenvalue h bar k. Instead, if we do the same, if we apply the same procedure to the standing waves, so we compute minus I h bar d over dx of a times sine of kx, we have that minus I h bar a and then k cosine of kx. So we don't find the same wave function. We find a different function that is a times cosine of kx. Therefore, the wave function psi of x in the standing wave case is not an eigenfunction of the momentum operator. This is the main difference between the two cases. And this, as the exercise states, should give you some insight into why periodic boundary conditions are a better choice for electrons in solids. So, standing waves allow only to have states with average velocity equal to 0. And they are not eigenfunctions of the momentum operator. Instead, we would like to be able to capture also the motion of the electrons inside the solid, right? Because if you want to study the conduction on a solid, we need traveling waves. And therefore, we need a description with wave functions that can have a non-zero eigenvalue, a non-zero expectation value for the momentum operator. Even better, if the eigenfunctions, if the wave functions are eigenfunctions of the momentum operator, we have a well-defined value, which is the eigenvalue of the momentum associated to each of these wave functions. So you understand now that to be able to describe electrons that can travel in a solid, we need a wave function that can travel, so that can have a non-zero expectation value of the momentum, of the linear momentum. And therefore, the periodic boundary conditions are surely a better choice than standing waves. Finally, concerning the position operator, it's clear that, at least in periodic boundary conditions, this kind of wave function psi of x cannot be a wave function, an eigenfunction of the position operator, because of the uncertainty principle. Indeed, if this eigenfunction psi of x is already an eigenfunction of the momentum operator, this means that at each measurement we have our momentum is very well defined and we don't have any uncertainty on it. So, because of the uncertainty principle, we need to have a non-zero uncertainty, of course, on the position to fulfill the Heisenberg uncertainty relation. And this means, therefore, that this wave function cannot be an eigenfunction of the position operator. Otherwise, we would have a measurement of the position that has zero uncertainty, and in that case, we would end up with an absurd result in which we have both the momentum and the position that have no uncertainty, which is, of course, which breaks, of course, the uncertainty principle. For the standing wave case, you can easily see that the position operator, the wave function is not an eigenfunction of the position operator. This is it for this exercise. If there are questions, of course, I am available to discuss, so feel free to drop me an email in case, or just come to my office and ask.